see both functional and non-functional approaches in the framework is historical. List t.sort predates link, which marked a decisive turn in functional direction. Writing programs with strong guarantees. Of the two concepts we just discussed, functions as first-class values initially seems more exciting, and will concentrate on it in the later part of this chapter. But before we move on, I'd like to briefly demonstrate why avoiding state mutation is also hugely beneficial, as it eliminates many complexities caused by mutable state. Let's look at an example. We'll revisit these topics in more detail, so don't worry if not everything is clear at this point. Type the following code into the repo. Listing 1.3. Mutating state from concurrent processes yields unpredictable results. This allows you to call range and write line without full qualification. This executes both tasks in parallel. Here you define nums to be a list of all integers between 10,000 plus and negative 10,000. Their sum should obviously be 0. You then create two tasks. Task 1 computes and prints out the sum. Task 2 first sorts the list and then computes and prints the sum. Each of these tasks will correctly compute the sum if run independently. When you run both tasks in parallel, however, task 1 comes up with an incorrect and unpredictable result. It's easy to see why, as task 1 reads the numbers in the list of compute to compute the sum. Task 2 is reordering that very same list. That's somewhat like trying to read a book while somebody else flips the pages. You'd be reading some well-mangled sentences. Graphically, this can be illustrated as shown in figure 1.1. What if we use link order by method instead of sorting the list in place? As you can see, using links functional implementation gives you a predictable result. Even when you execute the tasks in parallel, this is because task 3 isn't modifying the original list, but rather creating a completely new view of the data. Which is sorted. Task 1 and task 3 read from the original list concurrently, but concurrent reads don't cause any inconsistencies as shown in figure 1.2. This simple example illustrates a wider truth. When developers write an application in the imperative code style, explicitly mutating the program state, and later introduce concurrency due to new requirements or a need to improve performance, they inevitably face a lot of work and potentially some difficult bugs. When a program is written in a functional style from the outset, concurrency can often be added for free or with substantially less effort. We'll discuss state mutation and concurrency more in chapter 2 and 9. For now, let's go back to our overview of FP. Although most people will agree that treating functions as first-class values and avoiding state mutation are fundamental tenets of FP, their application gives rise to a series of practices and techniques, so it's debatable which techniques should be considered essential and included in a book like this. I encourage you to take a pragmatic approach to the subject and try to understand FP as a set of tools that you can use to address your programming tasks. As you learn these techniques, you'll start to look at problems from a different perspective. You'll start to think functionally. Now that we have a working definition of FP, let's look at the C# language itself and at its support for FP techniques. Functional versus object-oriented. I'm often asked to compare the contrast FP with object-oriented programming, OOP. This isn't simple, mainly because there are many incorrect assumptions about what OOP should look like. In theory, the fundamental principles of OOP, encapsulation, data abstraction, and so on, are orthogonal to the principles of FP. So there is no reason why the two paradigms can be combined. In practice, however, most object-oriented OO developers heavily rely on the imperative style in their method implementations, mutating state in practice in place and using explicit control flow. They use OO design in the large and imperative programming in the small. So the real question is that of imperative versus functional programming, and I'll summarize the benefits of FP and at the end of this chapter. Another question that often arises is how FP differs from OOP in terms of structuring a large complex application. The difficult art of structuring a complex application relies on several principles. Modality, modularity, dividing software into reusable components, separation of concerns. Each component should do only one thing. Layering, higher level components can depend on low level components, but not vice versa. Loose coupling, changes to a component shouldn't affect components that depend on it. These principles are generally valid regardless of whether the component in question is a function, a class, or an application. They are also in no way specific to OOP, so the same principles can be used to structure an application written in the functional style. The difference will be in what the components are and what APIs they expose. In practice, the functional emphasis on pure functions, which we'll discuss in chapter 2, and composability, chapter 5, make it significantly easier to achieve some of these design goals. How functional a language is C#. Functions are indeed first-class values in C#, as demonstrated in the previous listings. In fact, C# had support for functions as first-class values from the earliest version of the language through the delegate type, and the subsequent introduction of lambda expressions made the syntactic support even better. We'll review the language features in the next section. There are some quirks and limitations, such as when it comes to type inference. We'll discuss this in chapter 8, but overall, the support for functions as first-class values is pretty good. As for supporting a programming model that avoids in-place updates, the fundamental requirement in this area is that a language have garbage collection, because you create modified versions rather than updating existing values in place. You want all versions to be garbage collected as needed. Again, C# satisfies this requirement. Ideally, the language should also discourage in-place updates. This is C#'s greatest shortcoming. Everything is mutable by default, and the programmer has to put in a substantial amount of effort to achieve immutability. Fields and variables must explicitly be marked randomly to prevent mutation. Read only to prevent mutation. Compare this to F#, where variables are immutable by default and must explicitly be marked mutable to allow mutation. What about types? There are a few immutable types in the framework, such as string and date type, but language support for user-defined immutable types is poor. Although, as you'll see next, it has improved in C# 6 and is likely to improve further in future versions. Finally, collections in the framework are mutable, but a solid library of immutable collections is available. In summary, C# has very good support for some functional techniques, but not others. In its evolution, it has improved and it will continue to improve its support for functional techniques. In this book, you'll learn which features can be harnessed and also how to work around its shortcomings. Next, we'll review some language features from past, present, and upcoming versions of C# that are particularly relevant to FP. The functional nature of LINQ. When C# 3 was released, along with version 3.5 of the .NET Framework, it included a host of features inspired by functional languages, including the LINQ library, system.link, and some new language features enabling or enhancing what you could do with LINQ, such as extension methods and expression trees. LINQ is indeed a functional library. As you probably noticed, I used LINQ earlier to illustrate both tenets of FP. And the functional nature of LINQ will become even more apparent as you progress through this book. LINQ offers implementations for many common operations or lists, or more generally, or sequences, as instances of IEnumerable should technically be called. The most common of which are mapping, sorting, and filtering. See the common operations on sequences sidebar. Here is an example combining all three. Notice how where order by and select all take functions as arguments and don't mutate the given IEnumerable, but return a new IEnumerable instead, illustrating both tenets of FP you saw earlier. LINQ facilitates querying not only objects in memory linked to objects, but various other data sources like SQL tables and XML data. C# programmers have embraced LINQ as the standard toolset for working with lists and relational data, accounting for substantial amount of typical code base. On the upside, this means that you'll already have some sense of what a functional libraries API feels like. On the other hand, when working with other types, C# programmers generally stick to the imperative style of using flow control statements to express their program's intended behavior. As a result, most C# code bases I've seen are patchwork of functional style when working with IEnumerable and IVariables, and imperative style everything else. What this means is that although C# programmers are aware of the benefits of using a functional library such as LINQ, they haven't had enough exposure to the design principles behind LINQ to leverage those techniques in their own designs. That's something this book aims to address. Common operations on sequences. The LINQ library contains many methods for programming common operations on sequences such as the following. Mapping. Given a sequence and a function, mapping yields a new sequence with elements obtained by applying the given function to each element in the given sequence. In LINQ, this is done with the select method. consisting of the elements from the given sequence that pass the predicate in link where. Sorting given a sequence and a key selector function, sorting yields a new sequence ordered according to the key. In link order by and order by descending. Functional features in C#6 and C#7. C#6 and C#7 aren't as revolutionary as C#3, but they include many smaller language features that, taken together, provide a much better experience and more idiomatic syntax for coding function. Note: most features introduced in C#6 and C#7 offer better syntax, not new functionality. If you are using older version of C#, you can still apply all of the techniques shown in this book with a bit of extra typing. However, these newer features significantly improve readability, making programming in a functional style more attractive. You can see these features in action in the following listing. Listing 1.4. C#6 and 7 features relevant for FP. Using static enables unqualified access to the static members of system.math, like pi and pow. Getting only auto property can be set only in constructor. Getter only auto property can be set only in constructor. An expression bodied property. A local function is a method declared within another method. C#7 tuple syntax with named elements. Importing static members with using static. The using static statement in C#6 allows you to import the static members of a class. In this example, system.math class. As a result, in this example, you can invoke pi and pow members of math without further qualification. Why is this important? In FP, we prefer functions whose behavior relies only on their input arguments because we can reason about the test. These functions in isolation contrast with the instance method whose implementation typically interacts with instance variables. These functions are implemented as static methods in C#. So a functional library in C# will consist mainly of static methods. Using static allows you to more easily consume such libraries, and although overuse can lead to namespace pollution, reasonable use can make for clean, readable code. Easier immutable types with getter-only auto properties. When you declare a getter-only auto property, such as radius, the compiler implicitly declares a read-only bucking field. As a result, these properties can only be assigned a value in the constructor or inline. Getter-only auto properties facilitate the definition of immutable types, which you'll see in more detail in chapter 9. The circle class demonstrates this. It only has one field, the bucking field of radius, which is read-only. So once it's created, a circle can never change. More concise functions with expression-bodied members. The circumference property is declared with the expression body introduced with equals arrow, let's see, rather than with usual statement body in. Notice how much more concise this is compared to the area property. In FP, we tend to write lots of simple functions, many of them one-liners, and then compose them into more complex workflows. Expression-bodied methods allow you to do this with minimal syntactic noise. This is particularly evident when you want to write a function that returns a function, something you'll do a lot in this book. The expression-bodied syntax was introduced in C#6 for methods and properties, and it was generalized in C#7 to also apply to constructors, destructors, getters, and setters. Local functions. Writing lots of simple functions means that many functions are called from one location only. C#7 allows you to make this explicit by declaring methods within the scope of a method. For instance, the square method is declared within the scope of the area getter. Better syntax for tuples. Better syntax for tuples is the most important feature of C#7. It allows you to easily create and consume tuples, and most importantly, to assign meaningful names to their elements. For example, stats property returns a tuple of type double and specifies meaningful names by which its elements can be accessed. Tuples are important in FP because of the tendency to break tasks down into very small functions. You may end up with a data type whose only purpose is to capture the information returned by one function, and that's expected as input by another function. It's impractical to define dedicated types for for such structures, which don't correspond to meaningful domain abstractions. That's where tuples come in. More functional future of C#. As I was writing the first draft of this chapter in early 2016, development of C#7 was in its early days, and it was interesting to see that all the features for which the language team had identified strong interest were features normally associated with functional languages. They included the following: record types, boilerplate free immutable types, algebraic data types, a powerful addition to the type system, pattern matching, similar to a switch statement that works on the shape of the data, such as its type, rather than just a value. Better syntax for tuples. On one hand, it was disappointing that only the last item could be delivered. C#7 also includes a limited implementation of pattern matching, but it's a far cry from the kind of pattern matching available in functional languages, and it's generally inadequate for the way we'd like to use pattern matching when programming function. See section 10.2.4. On the other hand, these features are still on the table for future versions, and work has been done on the respective proposals. This means we are likely to see record types and more complete implementation of pattern matching in future versions of C#. So C# is poised to continue in its evolution as a multi-paradigm language with an increasingly strong functional component. This book will give you a good foundation for keeping up with the evolution of the language and the industry. It will also give you a good understanding of the concepts and motivations behind future versions of the language. Thinking in functions. In this section, I'll clarify what I mean by function. I'll start with the mathematical use of the word and then move on to the various language constructs that C# offers to represent functions. Function as maps. Functions as maps. In mathematics, a function is a map between two sets, respectively called the domain and codomain. That is, given an element from its domain, a function yields an element from its codomain. That's all there is. It doesn't matter whether the mapping is based on some formula or is completely arbitrary. In this sense, function is a completely abstract mathematical object, and the value that a function yields is determined exclusively by its input. You'll see that this isn't always the case with functions in programming. For example, imagine a function mapping lowercase letters to uppercase counterparts. As in figure 1.3, in this case the domain is the set ABC and the codomain is the set ABC capital. Naturally, there are functions for which the domain and codomain are the same set. Can you think of an example? How does this relate to programming functions? In statically typed languages like C#, the sets, domain and codomain, are represented with types. For example, if you code the function above, you could use char to represent both the domain and codomain, and type of your function could then be written as char. This is the function maps chars to chars, or equivalently, given a char, it yields a char. The types of the domain and codomain constitute a function's interface, also called its type or signature. You can think of this as a contract. A function signature declares that given an element from the domain, it will yield an element from the codomain. This may sound pretty obvious, but you'll see in chapter 3 that in reality, violations of the signature contract abound. Next, let's look at ways to encode the functions themselves. Representing functions in C#. There are several language constructs in C# that you can use to represent functions. Methods, delegates, lambda expressions, dictionaries. If you are well versed in this, skip to the next section, otherwise, here is a quick refresher. Methods. Methods are the most common and idiomatic representation of functions in C#. For example, the system.math class includes methods representing many common mathematical functions. Methods can represent functions, but they also fit into the object-oriented paradigm. They can be used to implement interfaces, they can be overloaded, and so on. They are constructs that really enable you to program in functional style are delegates and lambda expressions. Delegates. Delegates are type-safe functions, function pointers. Type-safe here means that a delegate is strongly typed. The types of the input and output values of the function are known at compile time, and consistency is enforced by compiler. Creating a delegate is a two-step process. You'll first declare a delegate type and then provide an implementation. This is analogous to writing an interface and then instantiating a class implementing that interface. The first step is done by using delegate keyword and providing the signature for the delegate. For example, .NET includes the following definition of a comparison T delegate. As you can see, a comparison T delegate can be given two T's and will yield an int indicating which is greater. Services in the OO sense are an extension of this idea. A set of functions with their respective input and output types, or more precisely, methods, which are essentially functions that take this, the current instance, as an implicit argument. Once you have a delegate type, you can instantiate it by providing an implementation like this. Provides an implementation uses the company's own delegate as an argument to sort. As you can see, a delegate is just an object, in the technical sense, that represents an operation, in this case, a comparison. Just like any other object, you can use a delegate as an argument for another method, as in listing 1.6. So delegates are the language feature that makes functions first-class values in C#. The func and action delegates. The .NET framework includes a couple of delegate families that can represent pretty much any function type. Func_R represents a function that takes no arguments and returns a result of type R. Funct_1R represents a function that takes an argument of type T1 and returns result of type R. Funct_T1T2R represent a function that takes a T1 and T2 and returns an R. And so on. There are delegates. These are delegates to represent functions of various articles. See the function arity sidebar. Since the introduction of func, it has become rare to use custom delegates. For example, instead of declaring a custom delegate like this, delegate greeting greeter person P, you just use the type func person greeting. The type of greeter in the preceding example is equivalent to or compatible with func person greeting. In both cases, it's a function that takes a person and returns a greeting. There's a similar delegate family to represent actions. Functions that have no return value, such as void methods. Action represents an action with no input arguments. Action T represents an action with an input argument of type T1, action T1, T2, and so on represents an action with several input arguments. The evolution of .NET has been away from custom delegates in favor of the more general func and action delegates. For instance, take the representation of a predicate. In .NET 2, a predicate delegate was introduced, which is used, for instance, in the findAll method used to filter a list T. In .NET 3, there were method also used for filtering, but defined on the more general enumerable T takes not a predicate T but simply a func T bool. Both function types are equivalent. Using func is recommended to avoid a proliferation of delegate types that represent the same function signature, but there is still something to be said in favor of the expressiveness of custom delegates. Predicate T, in my view, conveys intent more clearly than func T bool, and is closer to the spoken language. Function arity. Arity is a funny word that refers to the number of arguments that a function accepts. Annularity, function takes no arguments. A unarity, function takes one argument. A binarity, function takes two arguments. A ternarity, function takes three arguments, and so on. In reality, all functions can be viewed as being unary, because passing n arguments is equivalent to passing an n double as the only argument. For example, addition. Like any other binary arithmetic operation, is a function whose domain is the set of all pairs of numbers. Lambda expressions. Lambda expressions, called lambdas for short, are used to declare a function in line. For example, sorting a list of numbers alphabetically can be done with a lambda like so. If your function is short and you don't need to reuse it elsewhere, lambdas offer the most attractive notation. Also, notice that in the preceding example, the compiler not only infers the type of x and y to be int, it also converts the lambda to the delegate type comparison int expected by the sort method. Given that the provided lambda is compatible with this type, a predicate is a function that, given a value, say an integer, tells you whether it satisfies some condition, say whether it's even. Just like methods, delegates and lambdas have access to the variables in the scope in which they are declared. This is particularly useful when leveraging closures in lambda expressions. Here's an example. The pattern variable is referred from within the lambda and is therefore captured in closure. In this example, where expects a function that takes a day of week and returns a bool. In reality, the function expression expressed by the lambda expression also uses the value of pattern, which is captured in a closure to calculate its result. This is interesting. If you were to look at the function expressed by lambda with a more mathematical eye, you might say that it's actually a binary function that takes a day of week and a string, the pattern, as inputs and yields a bool. As programmers, however, we are usually mostly concerned about the function signature. So you might be more likely to look at it as a unary function from day of week to bool. Both perspectives are valid. The function must conform to its unary signature, but it depends on two values to do its work. Dictionaries. Dictionaries are fittingly also called maps or hash tables. They are data structures that provide a very direct representation of a function. They literally contain the association of keys, elements from the domain, or values, the corresponding elements from the domain, from the codomain. We normally think of dictionaries as data, so it's enriching to change perspectives for a moment and consider them as functions. Dictionaries are appropriate for presenting functions that are completely arbitrary, where the mappings can be computed but must be stored exhaustively. For example, to map Boolean values to their names in French, you could write the following. C#6 dictionary initializer syntax. Function application is performed with a lookup. The fact that functions can be represented with dictionaries also makes it possible to optimize computationally expensive functions by storing their computed results in a dictionary instead of recomputing them every time. For convenience, in the rest of the book, I'll use term function to indicate one of the C# representations of a function. So keep in mind that this doesn't quite match the mathematical definition of the term. You'll learn more about the differences between mathematical and programming functions in chapter 2. Higher order functions. Now that you've got an understanding of what FP is and we've reviewed the functional features of the language, it's time to start exploring some concrete functional techniques. We'll begin with the most important benefit of functions as first-class values. It gives you the ability to define higher order functions, HOFs. HOFs are functions that take other functions as input or return a function as output, or both. I'll assume that you've already used HOFs to some extent, such as with LINQ. We'll use HOFs a lot in this book, so this section should act as a refresher and will possibly introduce some use cases for HOFs that you may be less familiar with. HOFs are fun, and most of the examples in this section can be run in the repo. Make sure you try few variations of your own along the way. Functions that depend on other functions. Some HOFs take other functions as arguments and invoke them in order to do their work. Somewhat like a company may subcontract some of its work to another company. You've seen some examples of such HOFs earlier in this chapter. Sort, an instance method of list. And where, an extension method of IEnumerable. List.sort, when called with a comparison delegate, is a method that says, okay, I'll sort myself as long as you tell me how to compare any two elements that I contain. Sort does the job of sorting, but the caller can decide what logic to use for sorting. To use for comparing. Similarly, where does the job of filtering, and the caller decides what logic determines whether an element should be included. You can represent the type of where graphically as shown in figure 1.4. Let's look at an idealized implementation of where. The task of iterating over the list is an implementation detail of where. The criterion determining which items are included is decided by caller. The where method is responsible for the sorting logic, and the caller provides the predicate. Which is the criterion based on which the IEnumerable should be filtered. As you can see, HOFs can help with the separation of concerns in cases where logic can't otherwise be easily separated. Where and sort are examples of iterated applications. The Hof will apply the given function repeatedly for every element in the collection. One very crude way of looking at this is that you're passing as argument a function whose code will ultimately be executed inside the body of a loop within Hof. Something you couldn't do by only passing static data. The general scheme is shown in figure 1.5. Hof data iteratively applies the function given as an argument. Optional execution is another good candidate for Hofs. This is useful when you want to invoke a given function only in certain conditions, as illustrated in figure 1.6. A Hof that conditionally applies the function given as an argument. For example, imagine a method that looks up an element from the cache. A delegate can be provided and can be invoked in case of a cache miss. This implementation is functionally correct, but it lacks the error checking and optimizations in the link implementation. The logic in onMiss could involve an expensive operation such as database call, so you wouldn't want this to be executed unnecessarily. The preceding examples illustrate Hofs that take a function as input, often referred as a callback or a continuation, and use it to perform a task or to compute a value. This is perhaps the most common pattern for Hofs, and it's sometimes referred to as inversion control. The caller of Hofs decides what to do by supplying a function, and the callee decides when to do it by invoking the given function. Let's look at some other scenarios in which Hofs come in handy. Adapter functions. Some Hofs don't apply the given function at all, but rather return a function somehow related to the function given as an argument. For example, say you have a function that performs integer division. You want to change the order of the arguments so that the divisor comes first. This could be seen as a particular case of a more general problem, changing the order of the arguments. You can write a generic Hof that modifies any binary function by swapping the order of its arguments. Technically, it would be more correct to say that swap args returns a new function that invokes the given function with the arguments in the reverse order. But all an can now modify the original division function by applying swap args. Playing with this sort of off leads to the interesting idea that functions aren't set in stone. If you don't like the interface of a function, you can call it via another function that provides an interface that better suits your needs. That's why I call these adapter functions. Functions that create other functions. Sometimes you write functions whose primary purpose is to create another function. You can think of them as function factories. The following example uses a lambda to filter a sequence of numbers, keeping only the divisible by 2. What if you want something more general, like being able to filter for numbers divisible only by n? You could define a function that takes n and yields a suitable predicate that will evaluate whether any given number is divisible by n. We haven't looked at a hof like this before. It takes some static data and returns a function. Let's see how you can use it. Notice how you've gained not only in generality but also in readability. In this example, you're using the is mod of to produce a function, and then you're feeding it as input to another hof, where, as shown in figure 1.7, you'll see many uses of hofs in this book. Eventually, you look at them as regular functions, forgetting that they are higher order. Let's now look at how they can be used in scenario closer to everyday development.